Hello, my name is Shahram Bandaharizadeh, and this presentation describes algorithms to display 3D illuminations using flying light specs. Here's the outline of the talk. I introduce flying light specs, 3D displays using them, and system architecture for building a 3D display. Based on this architecture, I present algorithms to display static and motion illuminations, failure handling of the flying light specs, and STAG to charge the battery of the flying light specs. I conclude by telling you the contributions of this paper and its future research directions. A flying light spec is a miniature drone configured with light sources that produce different colors and textures. I refer to them as FLSs. In addition to emitting the red, green, blue lights with adjustable brightness, an FLS is programmable. It communicates with other FLSs to implement decentralized algorithms and has sensors to position itself in a 3D volume. This volume is partitioned into display cells that account for FLS downwash. Downwash is a region of instability caused by the flight of an FLS that impacts the flight of another FLS entering this region. We assume an illumination cell consists of multiple display cells. In this figure, the illumination cell consists of 125 display cells. An FLS display may use a large number of FLSs to render an illumination in a fixed 3D volume. These illuminations provide true depth without requiring the users to wear virtual reality headsets or glasses. They are realized using swarms of FLSs. An FLS display either renders a point cloud or a point cloud sequence. A point cloud is a set of 3D points representing virtual and real worlds in multiple dimensions. A point includes spatial coordinates and attributes such as color. You are looking at a rose point cloud consisting of a sequence of 115 point clouds. It is rendered at 24 point clouds per second and has a display time of 4.8 seconds. Each point cloud consists of approximately 65,000 points. If a 3D display represented each point as an FLS, then it would require 65,000 FLSs to render this point cloud sequence. An FLS display is equivalent to today's data centers, where failure of the FLSs is the norm rather than an exception. Hence, algorithms designed for FLS displays must address this challenge in order to be practical. A contribution of our paper is the components of an architecture for the FLS display. Here's the organization of the components as the bottom of an FLS display that may sit either on a floor or a tabletop. The paper details the different components and their functionalities. Briefly, the green hangers house FLSs. The conveyor belt at the top is the garbage collector. Failed FLSs fall on the conveyor belt, and the conveyor belt deposits these failed FLSs into the terminuses at the two ends of this architecture. The dispatchers as yellow cylinders are used to deploy FLSs in order to render an illumination. FLSs fly into the orange cylinders to gain access to the charging station in red. The charging station may be wireless. Once an FLS is fully charged, it may fly into the hangars for storage. The black server blade below the charging station is a hub It has the processing, networking, and storage of the system, of the display. And it executes a software component named orchestrator that manages different components by implementing centralized and decentralized algorithms. Let's use this architecture to render static illuminations. The paper presents two algorithms, min-dist and quota balanced, to dispatch FLSs for static illuminations. The algorithms are a trade-off between distance traveled by FLSs versus the time to render the illumination. In this example, quota balanced renders an illumination significantly faster. However, it also causes FLSs to travel a significantly longer distance to render the illumination. Let's consider motion illuminations, point cloud sequences. A contribution of the paper is MOTIL, an algorithm that computes flight paths of FLSs to render a point cloud sequence. An objective of MOTIL is to minimize distance traveled by FLSs. It is a divide and conquer algorithm that constructs a 3D grid on each point cloud to compute travel paths. An important configuration parameter of MOTIL is the capacity of a cuboid. It impacts the total flight distance computed by MOTIL's flight paths. Here, the x-axis shows the point cloud IDs of the rose point cloud sequence. I'm showing you only the first 14 point clouds in the sequence. The y-axis is the total distance traveled by the FLSs to transition an illumination from one point cloud to the next. As you can see, a small cuboid size of 100 results in a longer flight distance as compared with a cuboid size of 1500. The cuboid size also impacts the execution time of MOTIL implemented using MATLAB. The cuboid size of 1500 is much faster than a smaller cuboid size. This is because it processes fewer intercuboid flight paths and spends less time constructing the cuboids. FLSs are mechanical devices that fail. Their failure may degrade the quality of a rendering by not illuminating one of its points. To minimize the impact of these failures on the quality of an illumination, we construct reliability groups with standby FLSs. In normal mode of operation, standby FLSs are dark. Once an FLS fails, the standby assumes its lighting responsibility and flight paths. The display, namely the orchestrator, deploys a new FLS to substitute for the standby. We assume each FLS has some local storage that contains the data describing its flight paths and lighting responsibilities. The standby uses either a parity or a replication technique to maintain this data. It is important for the FLSs that constitute a reliability group to be in close proximity of one another to minimize the travel time for the standby to the location of a failed FLS. This enhances the quality of an illumination. Next, I want to talk about STAG. STAG is a novel algorithm that staggers charging of FLS batteries as a function of time to minimize both the number of charging stations and the overall number of FLSs required to render an illumination. STAG assumes each FLS has a fixed flight time beta on a fully charged battery. Moreover, it assumes omega time units are required to fully charge a depleted FLS battery. Beta and omega have a significant impact on the number of FLSs required to render an illumination. For example, today's nano drones provide flight time of 5 minutes on a fully charged battery. They require 10 minutes to fully charge their batteries. With STAG, these drones increase the number of FLSs to render an illumination by more than 200%. If future drones increase their flight time fourfolds to 20 minutes and shrink the time to charge their batteries fourfolds to 2.5 minutes, then STAG reduces the number of extra FLSs proportionally to 12.5%. In other words, STAG scales as a function of beta and omega. Beta and omega also impact the number of STAG flags, which in turn controls the number of FLSs that are mid-flight traveling either from the illumination to the charging station or from a charging station to the illumination. With battery characteristics of today's drones, at least 218 FLSs will be in mid-flight. This number decreases proportionally with future FLSs that have longer flight times and shorter charging durations. So once again, STAG is scaling. In sum, the contributions of this paper include a collection of algorithms that display static and motion illuminations that consider limited flight time of FLSs on a fully charged battery and duration of time to charge the FLS battery. STAG is optimal in that it minimizes the number of extra FLSs required to render an illumination and the number of charging stations required to render the illumination. We handle FLS failures by maintaining standby FLSs that substitute for the failed FLSs. STAG also uses these standby FLSs. When an FLS flies back to charge its battery, its lighting responsibilities are assigned to the standby, while a fully charged FLS is deployed from the dispatcher to substitute, to essentially make the reliability group complete. FLS displays are an exciting area of research. We are extending this study in several ways. First, we are developing a positioning system for FLSs to compute their location in a display. Such a positioning system is essential to enable FLSs to execute the flight paths computed by quota balanced and motil. Second, with failure handling, we are developing algorithms to form reliability groups using motil's computed flight paths. These groups should expedite mean time to repair while FLSs render an illumination. Third, we are investigating the use of physics engines such as Gazebo and AirSim to simulate the flight paths computed by motil. Both our failure handling techniques and STAG require extra FLSs that fly back and forth from the illumination to a charging station or the terminus. The question is, what is the impact of these FLSs on the quality of a display? And how do we keep these FLSs out of the user's field of view? Fifth, techniques presented in this study assume FLSs are homogeneous, providing the same reliability, beta and omega settings. A key question is what happens when FLSs are heterogeneous? How do we change the techniques to accommodate these FLSs? Finally, we're investigating how a swarm of FLSs may implement encounter-type haptic interactions by generating force back against the user's touch. The resulting FLS matter is the building block of objects materialized in an FLS display. We make all our software and data used in the experiments reported in this paper available at the following GitHub URL. Thank you.